Testing. Testing. We present a method for estimating full-length motion trajectories. They're full length. These motion trajectories are full length. Let's see. They're full length. These motion trajectories are full length. All right. Audio is working. Stream is on. Happy Monday, everybody. Hope everybody had a good weekend today. We're going to be starting off the week with a paper on tracking. This is a motion tracking paper written by Cornell, Google Research, and UC Berkeley. So happy Monday. How's it going? Tracking everything everywhere all at once. This is of course, reference to a popular movie, which I think won some Everything Everywhere All at Once. Yeah, it's a pretty good movie. I thought it was interesting, but a little reference to that. Come out relatively recently here, 8th of June. And I think it's no coincidence that they have the pride flags, right? The rainbow flag from the Pride movement here in the U.S. So I think it is the Pride month, so kind of little show of support there. So let's see. We present a new method for estimating full-length motion trajectories for every pixel in a frame of a video. All right, so every pixel in every frame of a video. So I think the key word there is pixel. It's not necessarily a semantic concept, right? So you click on a tennis shoe and you want to track that tennis shoe, but the way that they formulate this problem, they're probably tracking the pixel, not necessarily the concept, but the idea is to track the concept, right? For clarity, we only show sparse trajectories for foreground objects, though our method computes motion for all pixels. Okay, so sparse trajectories refers to that here you only see, I don't know, maybe a couple dozen trajectories, but really the method is working for all the pixels. Our method yields accurate, coherent long-range motion even for fast-moving object and robustly tracks through occlusions as shown in the dog and the swing examples. So here in this example with the dog and this example with the swing, the dog goes past these posts, the person goes past this post, and it's able to track through that. There is a nice little website for this. Let's see if I can find it. Project page right here. So here you can actually see the videos of the tracking, and it does seem to work very, very well. And they actually even have a little demo that's very interesting here. You can actually put points. So you can let's put a point here on the background, a point here on the sock, and then a point here on the watch. And then you can see how those points are moved over time. So there is some drift there. You notice how the point that's on her watch has now become this point on her t-shirt, and then the sock has kind of moved into the shoe. So right here it kind of shows you the best example of that, right? The point on her watch has almost completely disappeared. So there's a little bit of error, but you know the occlusion part is pretty good. Yeah, right there where it goes through that post is quite impressive. And of course, I guess if you have this level of tracking, you can then use this as a kind of platform to do other things. And here they show you pseudo depth. And the interesting thing about this pseudo depth is it's based on tracking, so it's not true depth, right? It's almost like a foreground background kind of process going on. And they have some failure cases too. I like to see failure cases, you know. It's annoying when people cherry pick too much, but like these cases here with the failures, these are obviously very difficult. You have this dog kind of weaving in between posts, which is extremely difficult to do in terms of tracking. And then you have a person kind of rotating a bike around, and a bike is kind of this tangle of stuff that all kind of looks the same, so it makes sense that that would kind of have a hard time as well. Cool, so let's get into it. present a new test time optimization method. Test time to me means inference. Optimization at test time probably means that they're not actually learning or pushing gradients into their neural net. They might just be kind of changing the parameters of some kind of hyperparameter, or maybe they're just training an additional little multi-layer perceptron or something. For estimating dense and long-range motion from a video sequence. Prior optical flow or particle video tracking algorithms. This is whenever you hear tracking, optical flow is generally not too far behind, but this is basically the classic definition of what they're doing here, which is basically every point in the image, where does it move? So you see here, you have some image, you see there's a grid, right, a field here, and at each point there's a vector that shows you where the movement in that point is, right? So there's a lot of different ways of calculating optical flow. The simplest ones, kind of the oldest ones, are looking at frames that are near each other and then kind of using that, but people have come up with all these different ways of doing it. Particle video tracking typically operate within limited temporal windows, generally within just a couple frames, and you're kind of diffing frames like that. And of course, the more your video moves, the harder the problem becomes. So if you have a camera that's just looking and then you have something moving right in front of the camera, that's a significantly easier problem than if you're like moving the camera around like that. That generally tends to be way harder. And if you combine both of those things, it's even harder. Struggling to track through occlusions and maintain global consistency, we propose a complete and globally consistent motion representation dubbed OmniMotion. Globally consistent motion representation, OmniMotion, that allows for accurate full-length motion estimation of every pixel in a video. Full length, probably the full length of the video sequence, motion estimation, basically a trajectory in pixel space. OmniMotion represents a video using a quasi 3D, so 3D but not quite, canonical volume and performs pixel-wise tracking. So volume representation to me means 3D, which means NeRF, I'm thinking, and performs pixel-wise tracking via bijections. Bijections are a mapping where each point maps specifically to another point. Yeah, so for example here, bijection 1-to-1, so every point in one space maps to another point in another space. Surjection, it doesn't necessarily need to be 1-to-1, and then bijection is 1-to-1. So I think in the context of this paper, it's going to be frame 1 and then frame 2, so it's going to be like frame by frame. So, but this is just a mapping. So in the highest level mathematical definition of these terms, these are just two spaces, but in this paper, it's going to be 2 frames of a video, or maybe local and canonical space. So local could be the pixel space, and then canonical could be this 3D volume, this quasi 3D volume that they're talking about. This representation allows us to ensure global consistency, track through occlusions, and model any combinations of camera and object motion. Yeah, so here they're kind of referring to what I was saying, where if you're moving the camera and the object, it's more difficult than just moving the camera, and it's more difficult than just moving the object. Extensive evaluations on the TADVID benchmark, okay, so, or TAPVID benchmark, and real-world footage show that our approach outperforms prior state-of-the-art methods by a large margin, both qualitatively and quantitatively. So we'll see whether this is actually state-of-the-art or whether they just happen to pick a couple benchmarks that are so obscure that nobody's ever tried them. So we've seen this a little bit as a trend, unfortunately, in kind of some of these papers where people pick prior methods that are kind of older or maybe just limited, and then they claim state-of-the-art, but really it's because they're not testing and comparing to things that they should be. All right. Motion estimation methods have traditionally followed one of two dominant approaches: sparse feature tracking and dense optical flow. So sparse feature tracking versus dense optical flow, what they're kind of trying to piece out here is that in some techniques you have a sparse amount of things that you're tracking, right? So maybe one thing that's very common in older computer vision approaches are things like these sift features, right? Where you have usually corners and edges of an object that are very easy to recognize regardless of how the object is oriented. And then that means that you can find those same features across multiple frames, no matter how the movement happens. And then you can track those sparse features, right? So this kind of sift is just one feature. It's a scale invariant feature transform, but there's a bajillion other handcrafted sparse features that you could use for tracking. And then dense optical flow is, keyword there is dense, right? So a lot more. The amount of features in an individual frame is much higher. While each type of method has proven effective, neither representation fully models the motion of a video. Pairwise optical flow fails to capture motion trajectories over long temporal windows. So if you're using optical flow and just comparing one frame to another frame, you're not going to be able to do that for something significantly longer where the scene changes. Maybe this scene of a horse, right? Where is it? But some of these videos are longer and they change background, so traditional optical flow is not going to work super well. And then sparse tracking, of course, if you change the stuff in the video, it's not going to work well. A number of approaches have sought to close this gap, estimating both dense and long-range pixel trajectories. These range from methods that simply chain together two-frame optical flow fields. So you have an optical flow field, and then you have a two-frame version of it, and then you have some techniques that chain those together. Recent approaches that directly predict per-pixel trajectories. These methods all use limited context when estimating motion, disregarding information that is either temporally or spatially distant. Yeah, so basically, much like any video approach, it's very expensive to do things with a huge amount of frames, and videos have this problem where you can have 30 frames per second, 60 frames per second, right? A 10-second video at 30 frames per second is 300 frames, right? So there's this kind of fundamental problem where you can't fit the entire context inside any algorithm that you're running on a computer, right? So you're either going to have to pick something that's temporally constrained, in which you're only looking at a limited set of frames, which means you're really only looking at a second or a fraction of a second, or you're going to have to do some kind of you're going to have to break up the computation spatially, which means that maybe things that are not together in the video don't get tracked. There's no way for a signal to go between them. So the choice of either temporal or spatial priors, because the compute isn't good enough to fit the entire context of a video, is an outstanding problem in the video modality. This locality can result in accumulated errors over long trajectories and spatiotemporal consistencies in these motion estimates. Even when prior methods do not consider long-range context, they operate in the 2D domain. Yeah, generally in pixel space. So 2D here, pixel space means within the height and width of the image, right? Resulting in a loss of tracking. All in all, producing both dense and long-range trajectories remains an open problem with three key challenges: maintaining accurate tracks across long sequences, tracking points through occlusions, and maintaining coherence in space and time. Okay, so coherence, long sequences, and occlusions. These are kind of the basic problems in the tracking world. In this work, we propose a holistic approach to video motion estimation that uses all the information in a video to jointly estimate a full-length motion trajectory for every pixel. Right? So no longer are you doing it for a limited set of features, such as here I'm showing sift features, right? Maybe you would only do it for whatever this is, maybe like 12 different features. Now you're doing it for every single pixel in the image. Our method, which we dub OmniMotion, uses a quasi 3D representation in which a canonical 3D volume is mapped to per frame local volumes through a set of local canonical bijections. Okay, so again, we said bijection is mapping from one space to another space, but in a one-to-one manner. So every single point in one thing has a corresponding point in another thing. So originally I thought that meant frame to frame, but the way that they're saying it here, they're calling it local canonical bijections. So they're basically going to have a local representation, right, which is per frame. So a 3D volume per frame, and then they're going to have a global, which there is the canonical 3D volume. So they're going to basically have like this world model and then a local model, and then they're going to have probably some losses that force the local and the global model to get together. These bijections serve as a flexible relaxation of dynamic multi-view geometry. Yeah, so I mean, this technique of having some kind of global state that you then improve over time with a bunch of different local approximations is very common. Like pretty much any kind of SLAM technique, any kind of photogrammetry technique is using some kind of idea like this, right? Our representation guarantees cycle consistency and can track all pixels even while occluded. We optimize our representation per video to jointly... Ooh, that's no good. So, per video, as soon as they said that, that to me indicates that you have to run this optimization process for the entire video. And once you do it for one video, that's it. You can't do it for a different video. So, this might end up having similar problems to NeRFs or other computer vision techniques and optimizations where you basically get something pretty out of it, but you have to basically redo it every time. So if you had a different video, you have to run their entire optimization again. Once optimized, a representation can be queried at any continuous coordinate in the video to receive a motion trajectory spanning the entire video. Queried at any continuous coordinate, this is kind of what we were seeing in the demo here. So if we go back to the demo, right, at any point in this video, you can, so this is the video, at any point you can say what is the, let's say this ear, and then there you go. It's actually not very good right here. You see her ear is actually there. What's actually kind of cool is you can actually probably do a whole neighborhood of points here. Let's see. Yeah, so none of these are actually on her ear. They're all kind of on the back of her head, which is no good. Yeah, that does not look good. But this is impressive, right? Whenever you actually go over this post, you see how all of them become this little X, which means it's occluded, which means to me that there's some kind of explicit occlusion, right? There's some notion of like, this is occluded, this is not occluded. We propose an approach that produces globally consistent full-length motion trajectories for all points. We can track points through occlusions, and we can tackle in the wild videos with any combination of camera and scene motion. I mean, we'll see about that. We demonstrate these strengths qualitatively on the TAP video tracking benchmark, where we achieve state-of-the-art performance. So let's actually look this up. TAP video tracking benchmark. Let's go on Papers with Code. Let's search up this video tracking benchmark. TAP vid. This is an optical flow estimation. You see here different benchmarks for optical flow. You have Kitty. Kitty is the autonomous vehicle benchmark. But I don't see any TAP benchmark here. TAPnet? Benchmark for tracking any point on a video. Is this on a website somewhere? Can we see it? No. Yeah, so unfortunately this seems like another situation where a benchmark created by here DeepMind, which of course is Google, so Google and DeepMind are basically, they're actually not just basically the same thing, they are the same thing. I think they actually joined those two groups together. So they get state-of-the-art, but they get state-of-the-art on a benchmark that pretty much only they compete in. So let's see. Related work, sparse feature tracking. Tracking features across images is essential for a wide range of applications, such as structure from motion, right? SLAM, simultaneous localization and mapping. And while sparse feature tracking can establish long-range correspondence, this correspondence is limited to a distinctive set of distinctive interest points, right? So this is the sparse, right? Where you're not doing it for every single pixel, you're doing it for a set of points that are that you can easily find, right? And for most of history, that's been constrained to edges and little corners and things like that, right? Because these edges and corners are easy to tell. But if you have something featureless, like maybe, for example, here in this picture, you see the back of this guy's wall, the ceiling, like there really isn't anything interesting here in this type of like featureless texture. So nobody has really done tracking for example, the pixel here, or maybe the pixel on this fan, because this entire fan kind of looks the same, right? Optical flow. Optical flow has traditionally been formulated as an optimization problem. However, recent advances in deep learning have enabled direct prediction of optical flow using neural networks. Yeah, I've seen this before, but optical flow is still kind of niche, you know. Sparse feature tracking is pretty common because any robotic application or photogrammetry, you're going to need to kind of have some notion of structure from motion or SLAM. Like, those are useful abilities, but optical flow is a little bit more niche. You don't really see that more often. Maybe if you work in autonomous vehicles or something like that. One leading method, Raft, estimates flow through iterative updates of a flow field based on 4D correlation volumes. Iterative updates of a flow field. Field there just means whenever you see flow, or whenever you see field, just think of a bunch of vectors sitting on a plane. So something like this, right? This is a field here. You see all these vectors, and then each of these vectors represents the motion of this point. And actually, this right here. So you see this is also optical flow. But red, green, and blue are often used indicative for 3 axes, right? X, Y, and Z. So red, green, and blue pixels here represent the direction of motion for each pixel here, right? It's kind of how similar to a normal map, right? If you guys have ever seen these normal maps that have this like weird red, green, blue coloring, what this red, green, blue coloring is telling you is the orientation of a vector that would be on the surface of this object, right? So for example, here, right, as you move around this cone, you see how the color changes in the vector. So optical flow can also be shown in that way, right, where you can basically use the color to indicate the direction of the arrow, just so you don't end up with something like this where the arrows are kind of hard to read. So optical flow can be a color like this, or it can be shown as a field of vectors. While optical flow methods allow for precise motion estimation between consecutive frames, they are not suited for long-range motion estimation. Yeah, they kind of it really only works well for frame by frame. Channeling pairwise optical flow to produce longer trajectories results in drift and fails to handle occlusions. And directly computing optical flow between distance frames often results in temporal inconsistency. Yeah, so I'm sure modern optical flow methods that use deep learning have tried to solve some of these problems before, but like optical flow is not, like, it doesn't actually have like knowledge of like what the fuck is actually underneath this. So if this car goes behind a tree, it is no like the optical flow algorithms have no notion of like it's the same car, right? They're just looking at little tiny patches of this image and then telling you, is that patch moving from this frame to the next frame, from this frame to the next frame? But the notion of like this is an object and this object is moving and so on, that doesn't exist in classic optical flow algorithms. Multi-frame flow. To move beyond the limitations of a 2-frame optical flow, a number of methods have explored multi-frame optical flow estimation. A notable recent approach, pips. It's probably not pip Python package, but what is this? 2022 paper on tracking through occlusion using point trajectories. Okay, so kind of relatively recent work, probably uses some amount of deep learning if I had to guess. Can estimate multi-frame by leveraging context within a wider temporal window. So kind of interesting, right? How a wider temporal window is considered 8 frames. So 8 frames, which at 30 frames per second is less than a third of a second, is considered a wide temporal window, right? So it just kind of goes to show you how limited and primitive our video techniques are. However, to produce motion for a video longer than this temporal windows, pips must still chain correspondences that is prone to drift, will lose track of points that remain occluded. Our method optimizes motion globally across the entire video, enabling a accurate long-range tracking, even through long periods of occlusion. Yeah, so I think kind of the important thing to realize here is that the reason these prior works are all kind of working with 2 frames or 8 frames is really just because of the compute budget, right? You can't fit an entire video into any kind of algorithm that's going to work in any amount of decent time, right? So you have to figure out some way to take the information in a frame and then basically compress it in such a way that you can have the entire video in some kind of representation, right? This canonical 3D volume that they're talking about, this is the global representation of the motion in that video. That thing needs to be able to fit inside and train in a reasonable amount of time. So then your problem becomes, okay, well, how do I get each individual frame to create some compressed representation? And then how do I take all these different compressed representations that I've created through this entire video and use them to optimize a single global compressed representation? And the constraints on all of that is that every single part of that needs to be able to fit on kind of basically one GPU and train in a reasonable amount of time. And as soon as you go into like full video frames, like the amount that you can actually fit is very small. So here in this previous work, which I haven't read this PIPS paper, but it seems like they managed to get to 8 frames, but 8 frames is still very, very short. You're not really going to be able to get much out of that, to be honest. Feature matching. While optical flow methods are typically intended to operate on consecutive frames, other techniques can estimate dense correspondences between distant pairs of video frames. But it's still pairs, right? So that's the problem. Several methods learn such correspondences in a weak or self-supervised manner using cues like cycle consistency, while others use stronger supervision signals such as geometric correspondences generated from 3D reconstruction pipelines. Okay, so a lot of references here. Basically, rather than doing what they're describing here, where you have 2 frames that are right next to each other, and then you basically look pixel by pixel and say, did this pixel move over here? Write this kind of flow field for very tight frames. People have tried to put all kinds of priors in, right? So self-supervised correspondences, so maybe you're feeding every single frame of a video into some kind of convnet and then looking at the little feature maps at every single point and then saying, hey, does this feature map kind of look like the feature map over there 50 frames down the line? Or, hey, let's take this frame, turn it into some kind of geometric kind of estimate of what's in this frame, and then we'll use that geometric estimate to compare to other geometric estimates that may be 50 frames down the line. However, pairwise matching approaches typically do not incorporate temporal context, which can lead to inconsistent tracking over long videos and poor occlusion handling. In contrast, our method not only enables smooth trajectories, but also produces plausible locations for occluded pixels. Yeah, so there's one paper that I really remember reading. It was like temporal contrastive learning. Yeah, this is a really cool paper, if you guys have ever seen this. This is a little bit older at this point, but similar to how you can use contrastive learning to learn clip, right? Where you're basically saying, hey, this text, when you embed this text and you embed this image, both of those points should be close together. people have used that same thing, but for videos where they're saying, hey, these two things in the video, right, should be similar together, and these things that are further away should be further away, right? So actually, here's the exact paper that I remember. So you have videos of the same thing, of this guy pouring water into a cup from different views, and then you have a network that's basically taking this frame and creating an embedding, and it's taking that same frame, and you know that these two frames are at the same point in time. So the same way that you're using contrastive learning to pull things together and push things apart in the kind of semantic space, what time contrastive networks are doing is they're basically pulling together things in the time and pushing away things that are further away in time. And then what you end up getting is a representation of this kind of thing that happened in time in such a way that there's a notion of like these two things are more similar than this thing. So this kind of like frame by frame, or correspondence, as I think is the word that they're calling here. Pairwise matching, never mind. Pairwise matching approaches. I think one of the coolest ones I've ever seen is this TCN, time contrastive networks. Video-based motion optimization. Most conceptually related to our approach are classical methods that optimize motion globally over an entire video. Particle video, for instance, can produce a set of semi-dense long-range trajectories called particles from initial optical flow fields. However, this method does not allow tracking through occlusions. The same visual entity will be treated as a different particle when it reappears after occlusions. This is sometimes called the re-ID problem. If you guys have ever done like tracking in for humans, this is something that happens all the time, right? Where basically you'll have these like dense scenes of humans that are walking with these security cameras, and the people who have these security cameras, one thing that they're very, very interested in is the ability to re-ID a person, right? So like I see a person kind of walk across one security camera, and then a different security camera catches them, and I don't want to just know, hey, this is a person. I want to be able to say this is the exact person that we saw 5 minutes earlier on this other camera, right? So honestly, like when I think about this, I feel like the technology for this is probably way more advanced than we think it is, but it's kind of within companies like SenseTime in China that are very, very good at this, right? I feel like the security camera re-ID technology that they use at SenseTime in China is probably way next level, right? Versus the things that we're used to using here. So for example, here's another kind of contrastive learning here where you're saying, hey, I have this data set where I know that this person and this person are, I guess, different, and then this person and this person are the same, so therefore pull the representations of these two people together and push these apart, and that gives me a basically, is this person the same or is this not the person the same? But re-ID. Further propose a combinatorial assignment. Is combinational a word? I feel like combinatorial is the actual word. Approach that can track through occlusions and generate longer trajectories. These methods only produce semi-dense track for videos with simple motion, whereas our method estimates long range motion for all pixels in the wild. Also related is particle SFM, SFM structure from motion, which also optimizes long-range correspondences from pairwise optical flows. Unlike our approach, particle SFM focuses on camera pose estimation within an SFM framework, where only correspondences from static regions are optimized and dynamic objects are treated as outliers. So, yeah, a lot of the time when people are interested in SFM, what they really want, as they mention here, is the camera pose. Because the reason they want the camera pose is because they want to be able to reconstruct what's inside the image, right? And in order to do that, you need to know how much the camera is moving from frame to frame. So I would actually say one thing they didn't mention here is CallMap. CallMap is actually probably the most popular approach for doing this. Like if you do any kind of photogrammetry, you're probably using CalMap. But let's see, free CalMap, a beginner tutorial. Okay, so this guy's just walking through it, but you basically feed in a bunch of pictures of like some thing where you walked around this building, and then the CalMap algorithm will basically solve this optimization, and it's not going to be perfect, but it'll roughly tell you where the camera was for every single frame. And the reason and the way that it's doing that is basically very similar to what they've been describing here, where it's finding these sparse features and then it's basically aligning those sparse features and then kind of just using simple triangles and geometry to figure out exactly where your camera is. But there was that period of computer vision, a bunch of these actually got patented. So I think, for example, orb features. Yeah, there was a bunch of these features back whenever people were hand designing these features where people started patenting these. So they started basically like making it illegal for other people to use this. And I think this is why CalMap became popular, because it was kind of like the equivalent for the MIT license. I don't know. I might also be talking out of my ass here, so but there's a lot of these different types of sparse features. Maybe it was Surf, the one that was patented. Dude, look at all. This is like a collection of ancient computer vision terms, like a Haar wavelet. Haar wavelets are the like edges, yeah. Diagonal edge, vertical edge, horizontal edge. Lines. Okay. We're getting distracted. Neural video representations. While our method shares similarities with recent methods that model videos using coordinate-based multi-layer perceptrons, MLPs, right? Just think about a little tiny neural net, basically. Prior work has primarily focused on problems such as novel view synthesis. So novel view synthesis, just a fancy way of saying generating images from a new view. So for example, a NeRF is a form of novel view synthesis, right? So you have a bunch of views of an object, and then you generate a novel view or new view from the NeRF. And video decomposition. In contrast, our work targets the challenge of dense long-range motion estimation. Though some methods for dynamic novel view synthesis produce 2D motion as a byproduct, these systems require known camera poses, and the resulting motion is often erroneous. Yeah, and I think these algorithms would work if the camera pose was known exactly. Like I think for some of these algorithms, if you actually, for example, put the camera on the end of a robot or on a robot that has a very, very good estimate of exactly what the position of that robot is, or exactly like robot arms are particularly good for this because they can not only tell you the XYZ position, but they can give you an exact yaw, pitch, and roll, right? An exact 60 position. So if you have like perfect 60 position from a robot arm, or maybe you have one of these like globes that has a ton of cameras that are all very, very precisely placed, then these algorithms are actually pretty good, right? Some of these more classic algorithms for reconstructing objects. But as soon as you have any kind of error in your camera poses, it all kind of just goes to shit. Alternatively, video decomposition-based representations such as layered neural atlases and deformable sprites. Okay, I've never heard about these, but they sound pretty badass. Solve for a mapping between frame and global texture alias atlas. Global texture atlas. So atlas to me means kind of like a code book, I guess. So maybe they have a code book of all the different textures that are in this video, and then you kind of do this almost like a nearest neighbor, if I had to guess. Frame-to-frame correspondences can be derived by inverting this mapping, but the process is expensive and unreliable. Furthermore, these methods are limited to representing videos using a limited number of layers with fixed ordering, restricting their ability to model complex real-world videos. We propose a test time optimization approach for estimating our dense and long-range motion. Our method takes as input a collection of frames and pairwise motion estimates. Okay, I would have liked it if it just took a collection of frames and that was it, but they also require pairwise noisy motion estimates. So they require kind of initial starting point, a guess. Complete globally consistent motion representation for the entire video. Once optimized, a representation can be queried with any pixel in any frame. Yeah, this is kind of the second time they mentioned this, but it's a very cool result. Our method identifies when points are occluded and even tracks points through occlusions. Identifies when points are occluding, so it's explicit and it tells you when the points are occluded, which is what we see here, right? There's an explicit notion of when it's occluded and when it's not occluded. We describe our underlying representation dubbed OmniMotion and then describe our optimization process. Okay, so OmniMotion representation. Classical representations of motion lose track of objects when they are occluded, can produce inconsistencies. To provide accurate, consistent tracks, we therefore need a global motion representation. Right? So you're going to have a bunch of different frames, and then each of those frames is going to contribute in some way to this global representation of the entire video, right? So this is what's going to be optimized over this process frame by frame. A data structure that encodes the trajectories of all points in a scene. One such global representation is the decomposition of a scene into a set of discrete depth-separated layers. So I don't know what they mean here. I think depth, they probably mean like channel, if I had to guess, right? Like RGB, sometimes D is added as an additional channel there, so maybe that's what they mean. There's layers in the sense of kind of the depth of a tensor, but they might literally mean depth as in like XYZ, like Cartesian space depth. Unfortunately, most real-world dynamic scenes cannot be represented as a set of fixed ordered layers. Consider the simple case of an object rotating in 3D. At the other extreme, a full reconstruction of that disentangles 3D scene geometry, camera pose, and scene motion. This, however, is an extremely ill-posed problem. Yeah, so it's difficult to have a good prior for this type of problem, right? Because there's a lot of different types of video, right? So this is kind of what they're hinting at here, where if you have a prior that assumes that kind of, for example, an object-centric prior, right? Where you're assuming that the camera is still and then there's an object that's moving. So this would be an example of kind of an object-centric prior here, right? The camera is basically still and then there's an object, in this case a dog, that is moving across the video. But that object-centric prior is not going to be very useful for something like, I don't know, maybe like this, right? I think like this one exactly, right? Where you have like the camera itself is moving, the objects are coming in and out of the frame, there's new objects, this like moped comes right in front, this guy comes right in front of that, so it's hard to find a prior that works for all these different types of videos. We answered this question using our proposed representation. OmniMotion represents the scene and as a canonical 3D volume that is mapped to local volumes for each frame through local canonical bijections, right? So this one-to-one mapping between local volumes and the canonical global volume. The local canonical bijections are parameterized as neural networks. Oh shit, look at that. That's kind of cool. So they have a neural network for each frame? No. A neural network for each per pixel? Let's see how many neural networks this actually is. Capture both camera and scene motion without disentangling the two. As such, the video can be considered as rendering of the result of local volumes from a fixed static camera. I don't know if this fixed static camera is a good prior there. OmniMotion does not explicitly disentangle camera and scene motion. Okay, the resulting representation is not a physically accurate 3D reconstruction. Instead, we call it a quasi-3D representation. This relaxation of dynamic multi-view geometry allows us to sidestep ambiguities that make dynamic 3D reconstruction challenging. So this is kind of interesting, right? Where they actually did mention this up here, how there's a bunch of approaches, a bunch of techniques for structure for motion where people are using these kind of geometric priors, right? Where they're saying, hey, even though this is a 2D video and it's just a bunch of 2D frames, we know for a fact that it's a video of a 3D Euclidean space, which is what our reality is, right? So we should be able to use that information, right? The fact that there's an actual 3D thing here and with depth, and that should allow us to basically put constraints on this optimization problem in order to find good correspondences. And it's interesting here that they're saying that they're not adding that constraint, right? They're basically saying we don't care if the 3D, if this quasi 3D representation that they're creating is actually physically accurate, right? And by relaxing, right, this kind of prior that the scene must represent the true 3D world, you're actually going to be able to get better results. So relaxing constraints results in a better approximation, which is kind of a cool idea there. We retain properties needed for consistent and accurate long-term tracking, establishing bijections between each local frame and a canonical frame. Ooh, okay, so this is not sounding good, right? So they said each bijection is parameterized by a neural network, and then here they say there's a bijection for each local frame and canonical frame. So the reason that doesn't sound good is because what that's telling me is that there's a neural net for every single frame. So that is a lot of neural nets. So I wonder how they're actually going to deal with that. Guarantees globally cycle-consistent 3D mappings across all local frames, which emulate the one-to-one correspondences between the real world. OmniMotion retains information about all scene points that are projected onto each pixel, along with their relative depth ordering, enable points to be tracked even when they are temporarily occluded. Okay, so here they're bringing up a difference between a scene point and a pixel. So scene point is probably going to be the actual semantic kind of object behind it. So here in this example, right, the scene point would be like the actual ear of the person versus the actual pixel, right? So this pixel is going to be separate from the actual scene point, right? So it knows that the person's ear is behind this post at this point. We describe our quasi-3D canonical volume and 3D bijections. We represent video content using a canonical volume G. Okay, so first little math definition there. We use green to highlight specific math definitions when we read these papers so that we can go back and check to see if we have seen that. As in NeRF, a neural radiance field, we define a coordinate-based network F theta. So you have a neural network F, right? A neural network is a function. It maps one thing to another thing, and the theta here represents the parameters of that neural network. Over G, that maps each canonical 3D coordinate. So here's a 3D coordinate, U in G, right? You have some point U inside this volume G to the density sigma and the color C. So let's pull up our good old NeRF picture here. NeRF computer vision. Yep, right here. But what a NeRF is doing is it's basically taking a single point, right? So this point here is represented by X, Y, and Z, 3 coordinates. You give that to this NeRF. Usually you're passing a couple other things too, such as the view of the camera, the view angle, and then the NeRF will give you a sigma, which is the density, right? Whether or not basically there's something there or whether there's nothing there. And then it'll also give you a color, which is an RGB. The density stored in G is key as it tells us whether the surfaces are in canonical space. Okay, so it seems like they might be overloading kind of the meaning of this density. In a NERF, generally this just means whether or not there is an object there. It's almost like a proxy for whether or not an object exists at this point in space. That's what the density in NERFs usually represent. But I think here, the way that they're saying this, it might also be kind of using it to reason about whether the scene points are in view or not in view. So we'll see whether this density is different from the NERF density. Together with the 3D bijections, Erland Hillman, what subject areas jobs involve working on this kind of research task and similar areas like NERF? So any kind of robotics, like if you're on doing robotics, you are interested in this type of stuff, like structure from motion, SLAM, which is the simultaneous localization and mapping, and then optical flow. So if you're in robotics, autonomous vehicles, anything like that. But I also think that there's a new space that's kind of being created now, this video generation, right? So there's like the entertainment industry is going into going into this world where you're going to have people that are going to be making videos with neural nets, right? So for example here, optical flow of a person jumping in a, I don't know, of a person, or let's try to recreate one of these. Person swinging on a swing. So I don't know. If you're only going to work in text world and you're a natural language person, you probably don't really need to give a shit about any of this. But if you're doing anything that involves videos, or if you're in robotics, I think this type of stuff is very interesting. So here, what I'm showing you guys, this is Runway ML. This is a company that does a bunch of generative AI tools, and they just recently released Gen 2, which is basically a video generation, text to video. I've been playing with it. It's still very primitive, so there's still a lot of room to grow. But here, let's see what we get here. Take a sip of this yerba mate. What if I made my own yerba mate brand? Would you guys watch that? So here we go. Here's some generative video. Does that look like a swing? It kind of looks like a swing, but doesn't look like anything to me. Looks like here this chain suddenly becomes the person. I don't know. Let's get back to the math here. Okay, bijections. We define a continuous bijective mapping. So continuous, right, means that it's not discrete. There's no separation. It's like there's a smooth, you can basically draw a smooth line from one thing to the next thing. Bijective mapping, again, one-to-one mapping from one to another. Actually, let's delete this here just so we can use the right color. Continuous bijective mapping TI should be green. That maps a 3D point XI from each local coordinate frame LI to the canonical 3D coordinate frame U. Okay, so note here how the 3D point XI is separate from the canonical 3D coordinate U, right? So U and XI, right? The U in G is not like actual 3D space. G is this like quasi 3D space. So they have a mapping which goes from actual 3D space XI into this quasi 3D space G. So XI is the point in real 3D space, U is the point in quasi space. I is the frame index, so if you have 5-second video, 30 frames per second, that's what the I is referring to. Note that the canonical coordinate u is time independent and can be viewed as a globally consistent index for a particular scene point. There's no notion of time in this quasi 3D representation, but I feel like this actually inherently limits the entire representation. So that's not very good right there, because what this is telling me is that this quasi 3D representation basically needs to encode the entire video, right? It needs to encode the entire video, which works great if you have a 6-second video like this, where basically it's just a car moving across the thing, right? And it's the same kind of, there's nothing, there's only one real thing in this video, you know what I'm saying? It's like, it's the same objects, the same background, the same foreground. So I think whenever you have time independent, that's only going to work for a particular type of video. I think if you were to take a video like this where you're spinning around, right? That's going to be much harder to kind of fit into a time independent quasi 3D representation. By composing these bijective mappings and their inverses, we can map a 3D point from one local 3D coordinate to another. So keyword here, their inverses, right? Which means that not only are they mapping from x to u, they're also mapping from u to x. So Li, Lj, so I and j are both indices to represent the frame. And you have here tj -1 times ti of xi. So what are they showing here in this equation? What they're showing you here in this equation is that if you use this mapping and you map that and you map the point xi, you're going to get a point ui. And if you use that point ui and you do the inverse mapping, instead, not for I but for j, the next frame, you're going to get xj. So this is telling you that the u that maps to xi and xj is the same u. And these mappings, of which there is basically one for every frame, tj, ti, the inverse allows you to go back and forth between the quasi space, which contains u, and the real space, which contains x's. Bijective mappings ensure that the resulting correspondences between 3D points and individual frames are all cycle consistent, as they arise from the same canonical point. Yeah, but I guess, like, to me, what I don't like about this is that you're limited. You have whatever the capacity of your representation to store canonical points is, you're limited at some point, right? At some point, if the video has more scene points, I don't know what the right terminology is here, but if the video has more scene points and a lot of different semantic concepts, it's going to be difficult to have the amount of capacity required to have a canonical point for every single thing in that video. This allows for expressive maps that can capture real-world motion. We parameterize these bijections as invertible neural networks. Okay, so every single one of these ti, tj, and there's going to be however many frames there are, is going to be a neural net. Inspired by recent work on homeomorphic shape modeling, we use real NVP. What is real NVP? Density estimation using real NVP. This is Sami Bengio, which is Yoshua Bengio's brother. Yeah, if you guys didn't know this, the Yoshua Bengio dude has a brother who also works in this guy. So it's kind of weird. There's two of them. But okay, let's actually look this up though. Real NVP. Density estimation using real NVP. Actually, here we go. Papers with code. Real NVP explain. Real NVP is a generative model that uses real valued, non-volume preserving transformations for density estimation. The model can perform efficient and extract inference, sampling, and long density estimation of data points. Real NVP learns an invertible stable mapping. So I think the keyword here is the invertible, the fact that you can go from the data space X into the latent space and then back to the latent space. Right, so here they're calling it inference versus generation, but I think the main takeaway here is that basically this function f can go from x to z, and then the inverse of f can go from z to x. So what does the inverse of a neural net mean? How do you take the inverse of a neural net? Do you literally just run it backwards? Real MVP builds bijective mappings by composing simple bijective transformation called affine coupling layers. An affine coupling layer splits the input into two parts. The first part is left unchanged, but is used to parameterize an affine transformation that is applied to the second part. So affine transformation, whenever I see that, I think of like basically warping and scaling. Yeah, so there's actually a formal mathematical definition for this, but let's see. Affine transformation is a linear mapping method that preserves points, straight lines, and planes. Yeah, so whenever I think affine in my head, I'm thinking this. You know, like you basically take a grid and then you basically just warp it into this. But obviously you can see here how the affine transformation is preserving the points, it's preserving the lines. Okay. So they have an affine transformation, and then half of it is being used to define that, and then they apply it. Okay, so I still don't really know exactly what they're doing here, but it seems like the key word here is the invertible, right? That's really what they care about, is the invertible nature of this, because that's their whole kind of quasi 3D mapping depends on the ability to be able to invert and go back and forth between them. Hey man, I really do do a lot of good streams. I often watch your paper decomposition. They're really helpful. Although I find reading papers alone very tough, but I think it's a learning process. Yeah, I think it, like, don't get discouraged, you know, and I hope that, like, sometimes you watch videos and the people just kind of seem to magically know what's going on, and it's not that they actually magically know and they're like 10 times smarter than you. It's really just that they basically went through the paper much like I'm doing now, and they just have like 50 tabs open and they're like looking up like, oh, what's real MVP? And then they read about real MVP and then they go back to the paper. So a lot of people will hide that from you and they'll make it seem as if they just know everything that there is to know, right? But that's not the case. Really, if you're reading papers, you're constantly opening up new tabs and searching what the fuck is real MVP? Like, what does an invertible neural network mean, and so on. So don't get discouraged if you, like, it takes you very long to get through a paragraph, right? And sometimes that happens. Sometimes you read a paper and you only get through a couple paragraphs. You know, it's like it's so dense and there's so many new terms that you don't know what they are that it takes you a while to even just get through a couple paragraphs, and that's totally fine. You know, because understand that every single paper is like is basically on the bleeding edge of some specific field of machine learning or whatever it is, right? So realize that, like, the person who wrote this paper has a PhD in this specific type of machine learning. So if you're reading a huge variety of different papers, it's very unreasonable to assume that you're enough of an expert in all of those things to understand all of those things, right? So I don't know, TLDR, don't worry about not understanding everything, because it's literally impossible for a single human to understand everything. Okay, so we modify this architecture to condition on a per frame latent code. Okay, so not only do they have this invertible neural network, but they're also going to be conditioning on, right, which means that they're feeding in some additional piece of information into this neural net, right? When the neural net performs inference, it's also going to be given something else, and what they're going to be giving it is this latent code psi here, right? I'm pretty sure that's psi. Psi, Greek letter. Yeah. When all invertible mappings, Ti, are parameterized by the same invertible network, M theta. Okay, all right. So you see, this is good. This is good. Because up until now, the way that they were making this sound, they were making it sound like they literally had a neural network for every single frame of this video, right? They were saying, okay, you have these bijections, which are parameterized by neural nets. You have a different bijection for every single frame. And I'm like, this is not sounding good. This is sounding like they're literally going to have like 100 different neural nets. But now here, you finally learn the truth, is that every single one of those bijections are going to actually be the same neural network. There's only going to be one neural network here. It's going to be M theta, right? So theta is going to be the parameters for this neural network M. And this neural network M takes in whatever this is going to be, right? Xi, but then it's also going to take this latent code. All right, so that actually seems pretty straightforward. Computing frame-to-frame motion. Given this representation, we now describe how we can compute 2D motion for any query pixel Pi. Okay, so you have the U, which is the scene point in the canonical quasi 3D space. You have Xi, which is the 3D point, and now you have Pi, which is the pixel. Intuitively, we lift the query pixels to 3D by sampling points on array, map these 3D points to a target frame J, and then render these mapped 3D points from a different samples through alpha compositing. So sampling points along array, that very much makes me think of the NeRF here, right? So what in a NeRF, you're sampling points along array. This red line here is array. Array is just a fancy word for a vector, right? There's a start point, and it's basically like an infinite vector. A vector like ends at a specific point, and there's a specific coordinate for that point, but array basically just keeps going to infinity. So you're sampling points along array, which is what they're describing here. But I think the ray here is not going through actual 3D space. I think it's going through their quasi 3D space. Finally project them back to 2D. What the fuck is a putative correspondence? I've never even heard that word, putative. Putative means generally believed, supposed, or assumed. Okay, so basically they're saying we do this and we should be able to get a correspondence, but that correspondence isn't 100% correct. It's putative, which basically means estimate. To obtain a estimate of a correspondence, right? I don't know why the fuck they chose to use the word putative. That's a very archaic, obscure word. I would have just used an estimate. Specifically, since we assume that a camera motion is subsumed by the local canonical bijections Ti, we simply use a fixed orthographic camera. I don't like that. I don't like this camera being fixed prior. That just does not feel good to me. The ray at Pi can then be defined as Ri. So this is the ray, right? You have some origin, and you have some direction. So the origin is the pixel, and then 0, I guess, maybe for the depth. And then D is the direction, and in this case, it seems like they're basically defining this quasi 3D space as a volume where the depth in that volume corresponds to this kind of like a notion of like what's in front of another thing, right? It's like a quasi 3D space, so it's not actually the 3D position of something. It's this kind of density which they're kind of... This is kind of super interesting because it's basically they're kind of doing a NeRF style volume representation, but in a NeRF volume representation, like you're actually trying to represent 3D space, right? You're actually trying to represent X, Y, and Z as they appear in our reality, right? But what they're doing here is they're basically doing a NeRF, but it's not actual 3D space. It's basically this like fake 3D space where X and Y are pixel coordinates, right? Pi, right? So X and Y in terms of pixel space, but then the depth is almost like this weird notion of like object is in front of another object or object is occluded, which is kind of weird to think about, but I like it. You know, it's unique. I haven't necessarily seen this before, so kind of cool. We sample K samples on the ray. Okay, so there's a set of K of these, right? So back to our NERF, right? Here you have 1, 2, 3, 4, 5, 6, 7 samples shown here. So K is the number of those samples. Equivalent to a corresponding set of depth values. Okay, so of course each sample you're going to have at different depth, right? And here the actual ray is perfectly straight inside this canonical space, right? Notice how the direction here is straight through. So in a normal NERF, right, you see how this ray is kind of angled, like you're generally not going to get a ray that goes perfectly basically perpendicular and orthogonal and parallel to the dimensions of the volume in a NERF. But here that seems like exactly what they're doing. The direction of the ray is basically perfectly flat, right? 0, 0, 1. And then the samples are along this depth in the volume. Despite not being a physical camera ray, it captures the notion of multiple surfaces at each pixel and suffices to handle occlusion. Yeah, it's just so... It's like you're almost compressing... It's very interesting. It's like basically an RGBD prior for a NERF as opposed to a Euclidean space prior, if that makes any sense. This is kind of like breaking my brain because now I'm like thinking about where else could you apply that? Could you apply that to... Could you do diffusion with a similar kind of prior? Probably. Next, we obtain densities and colors for these samples by mapping them to a canonical space and then querying the density network F theta. Taking the kth sample xi, so k as in the kth sample along this ray, and note how k and I are different because I corresponds to the frame, but k corresponds to the depth within this quasi 3D volume, which is basically the position in the video. Like, is it, for example, here here you have basically a point here, and then a point here, right? So you have this point on the ear, and then this point on the on this beam in front, and right here in this picture, they're probably both at the same depth, right? Because they're both visible. But then as soon as you go here, now they're at different depths. Now this point is very clearly in the front, and then this point is in the back. So that depth is kind of a notion of what's in the foreground and what's in the background. Its density and color can be rewritten as sigma k ck, so this is just the color and the density at a specific of that point. And this is basically, there's two functions here, two neural nets. So first neural net is this invertible neural net, which is mapping from a 3D point xik into or conditioned on this latent vector psi I. So you're giving both of those to this neural net m theta. That neural net m theta is producing a mapping. It's giving you a point u, right? ui, and then that ui point, you feed it into this neural net f theta, and that neural net f theta, which is basically the one that's like the NERF, right, is giving you the actual color and the density, sigma k and ck. We'll look at this picture in a second here. Let's finish the actual stuff here. We can also map each sample along the ray to a corresponding 3D location, x, k, j, and frame j. Yeah, so because this m theta is invertible, and you can basically do this little thing that they're doing here, where you can take a point in one frame and then basically find the corresponding point in a different frame, you can basically get this 3D location at any frame. We can now aggregate the correspondences x, j, k from all samples to produce a single correspondence x, j. So aggregate, and you have x, j, k, right? There's k of these, and you basically aggregate them together, and you have one, x, j hat here. So this is very similar to what you do in a NERF. In a NERF, you are sampling along this ray, but you're going to use ray marching, and ray marching is this. Basically, you could think of it like an easy way to think about it is you're basically adding up all these things here. You're basically saying, okay, well, the color at this pixel is going to be this plus this plus this plus this plus this plus this. It's a little bit more complicated than that because they're accounting for the opacity and the transmittance as you go along the ray, but like roughly at a high level, you're kind of accumulating all of these little samples and then getting one single pixel value from that, right? So for example, here, this is the final pixel value. And here they're doing a similar thing, right? They're aggregating all these points along this, all these samples along the ray xjk and aggregating them into one single point x hat. This aggregation is similar to how I should just finish reading this paragraph, but I know I like how I literally came to the same conclusion that they did. Similar to how the colors of a sample point are aggregated in a NeRF, we use alpha compositing with the alpha value for the kth sample as alpha k equals 1 minus exponent of negative sigma k. So alpha compositing is basically what you do in like Photoshop or something like that. Right? In Photoshop, generally you have, or any kind of like image manipulation stuff like that, you have the image itself, but then you also have what's known as the alpha map, and the alpha map basically tells you what's see-through and what's not see-through. So, for example, anytime you see an image that has like this like grid pattern in the back like that, right? That most of you probably already know this, but like this means that there's no background. It's like see-through. So there's an alpha map that's telling you here everything here is see-through and everything here is fully bold, right? And you can have more complicated kind of alpha maps that are like semi-transparent, and then that allows you to kind of do this compositing. So, whereas in a NeRF, you're basically having this you're ray marching across an actual 3D or an actual like 3D space that corresponds to an actual 3D volume that's corresponds supposedly to our physical reality, which is three-dimensional. Here they're just saying, okay, you have things that are foreground, background, alpha compositing. That's kind of a terrible explanation, and I wish I could kind of explain it better, but I feel like it's basically here's a better way to describe it. It's a 2.5D prior. So sometimes you hear this, 2.5D, right? 2.5D perspective refers to gameplay or movement that is restricted to two-dimensional plane, but there's kind of like a fake third dimension, right? This foreground, background. So that's my guess, that's my high-level explanation of what this entire paper is. It's basically a 2.5D NeRF. But okay, the alpha map for each kth sample is basically just this curve right here, 1 minus exponent. So this actually is very similar to the NeRF compositing here, right? You're summing over all k, where each sample x is multiplied by the alpha k, which is kind of like the transparency. And then you have this additional tk here, where the tk is the multiplication of 1 minus alpha. So like as you go further and further, right, you get these alpha terms multiply with each other, right? 1 minus. So let's say your alpha is 0.1 and you're going to get 1 minus 0.1, you're going to get 0.9. The next one might be 0.3 and you're going to get 0.9 times 0.3 times 0.2 times 0.7. Like, so like you keep multiplying these numbers that are less than 1 by each other, and you get a smaller and smaller and smaller number, which means that as you go deeper into the samples of this ray, the contribution from that is going to get less and less and less and less and less, right? Anytime you see a multiplication like this, so this is a addition, you're adding these things from 1 to k. This is you're multiplying them from 1 to k minus 1. Anytime you see a multiplication like this and you have 1 minus something, what is happening here is this number is basically getting smaller and smaller and smaller and smaller. A similar process is used to composite CK. So CK is the color. To get the image space color, C hat I for PI. So C hat I is the actual final color that you're going to be actually using. I don't know what C hat I is going to be used for, but that's the actual color in pixel space. X hat j is then projected using our stationary orthographic camera model to yield the predicted 2D corresponding location p hat j for the query location pi. All right. Seems pretty straightforward. All right, let's look at this figure 2 here now that we kind of understand what all these different terms are. Method overview. Our OmniMotion representation is composed of a canonical 3D volume G and a set of bijections Ti that map between each frame's local volume Li and the canonical volume G. So this Ti function here maps from Xi to the canonical 3D volume G, which they represent here as a cloud, right? And obviously the inverse maps from here to here, right? So you're using the actual Ti to go from here to here, and then you're using the inverse Tj to go from here to here, to go from U to Xj. Here you have 2 frames of a video. It doesn't matter. They don't need to be frames that are next to each other. They can be any 2 frames, right? So they can basically mess with the time distance between these 2 frames, which is probably what they're going to be doing in the optimization process. Here you have the actual ray that's going through, in this case, a 3D volume. And then you have the sample along that ray, xi. Here you have f theta. This is the little NeRF-like neural net that, given a point in this canonical 3D volume, it'll give you the color and the density. And this is almost like identical to the figure from the NeRF paper, but you see here they also have a plot here of the density as a function of distance along the ray. So here you have a plot of the density sigma as a x is the distance along the ray here, right? So you have however many samples along this ray, 1, 2, 3, 4, 5. This corresponds to the 1, 2, 3, 4, 5 points here. And you can see here how there's these spikes in density, which means that there's different objects at those points. Like here, there's some kind of object, and here there's nothing. And this is the compositing that they're talking about here. And once you composite all of these together, you get the actual final point p hat j, which is in pixel space. Alpha compositing and projecting. Any local 3D location xi in frame I can be mapped to its corresponding canonical location u, and then mapped back to another through the inverse mapping. Each location is associated with a color and density, computed using a coordinate frame MLP, coordinate-based MLP. So this is another problem too, right? Is that the correspondences are based around this assumption of visual similarity, right? Like, you could think of situations that would game this entirely, right? Think about a situation where, like, I'm holding something like this, you know what I'm saying? Like, I'm holding this, and then I move it, and then I go like this, I occlude it, I switch it around, and now it no longer has this logo on it, right? So, like, if I change something while it's occluded, this is going to completely fuck up this kind of thing, right? Like, let's say this person had a, like, I don't know, some kind of, like, yellow t-shirt underneath this, and then, like, as she passes through this beam, she removes and then has now a yellow t-shirt. It would completely fuck up all the correspondences. So, something to note there as well. To compute the corresponding 2D location for a given query point pi mapped from frame I to j. So you have these query points in pixel space. We shoot a ray into Li and sample a set of points. So you have your samples along that ray, which are then mapped first to the canonical space to obtain their densities, and then to frame j to compute their corresponding local 3D locations. These points are then alpha composited and projected to obtain the 2D corresponding location pj. Yeah, so really, ultimately what you're trying to do here is you're trying to say, what is this point pi? What is the corresponding point pj, right? That's all you're trying to do. You're trying to say, where is this point at this frame in a later frame? Our optimization process takes as input a video sequence and a collection of noisy correspondence predictions as guidance and generates a complete, globally consistent motion estimate for the entire video. Yeah, so I didn't like this. They mentioned this earlier, but it's not just taking a video sequence, right? It's actually they're seeding this, right? They're not just starting from zero. They're starting from an existing method. So they're basically going to use an already existing, probably classic approach to get noisy correspondences, which basically means noisy guesses, and then they're going to refine those guesses with their approach that they talked about here. So they're going to be using RAFT to compute input pairwise correspondences. So what is RAFT? RAFT is recurrent all-parallel field transforms for optical flow. Let's copy paste that. So this is the actual RAFT paper. It might even be some of the same authors on this if I had to guess. Zachary Teed and Jia Deng. Is that the same people? Let's see. Zachary G. Jia Deng. No, it's not. It's different people. Okay, that's kind of interesting. So RAFT is basically optical flow estimation. It seems like they're basically doing they're feeding each frame into a neural net and then kind of doing some kind of difference between them. I don't know. I don't actually know what RAFT is, but I'm just kind of like trying to get an idea from these pictures. But okay, so they use this RAFT, which is kind of an older algorithm, to get a guess for these correspondences, and then they're going to refine those correspondences with their technique. We also experimented with another dense correspondence method, TAP-net, and demonstrated in our evaluation that our approach consistently works well given different types of input correspondence. What does work well mean, right? That's kind of like a vague term. Taking RAFT as an example, we begin by exhaustively computing all pairwise optical flows. Ooh, that sounds gross. Since optical flow methods, Dogatahan. Hey, sorry for being late. Dude, no, it's fine, dude. You can come in late. You can leave. It doesn't matter. You know, nobody knows. Can produce significant errors under large displacements. We apply cycle consistency and appearance consistency to filter out spurious correspondences. We also optionally augment the flows through chaining when deemed reliable. I don't know what chaining is. I'm guessing they just, if they have pairwise correspondences between frames like 1 and 10 and then 10 and 20, maybe they like chain those together. Maybe that's what they're talking about. Additional details about our flow collection process are provided in the supplement material. Despite the filtering, the now incomplete flow fields remain noisy and inconsistent. We now introduce our optimization method that consolidates these noisy, incomplete pairwise motions into complete and accurate long-range motion. Okay, so they use an older technique to get a bunch of pairwise correspondences, and then they filter those out, right? Filter it out. They chain together any that are close together, and then they're going to actually use that as basically the starting point for their technique. Okay, so what are the different loss functions? And just peeking ahead here, you can see how the final loss that they're going to use in this optimization process is going to be composed of like 3 different losses here. You're going to have an L flow, an L fo, and an L reg. So, you know, so it's kind of like annoying to have different losses like this, because then basically you need to define these hyperparameters here, lambda fo and lambda reg. So these are weights that control the relative importance of certain losses, and you could just pick those, but that introduces a basically error because now you're picking specific values for these weights. If you want to be super fancy, you can change them over time, so you can have a schedule for these weights, which is something that people do sometimes, is these weights change over the course of training. So maybe at the beginning you don't have this regularization term, this lambda reg is very small, and then over time it gets bigger. So these hyperparameters, these lambdas, are generally not great because they just kind of make it difficult to solve your optimization problem, because now you have to either pick a specific value for them or choose some kind of schedule for them. Our primary loss function is a flow loss. We minimize the mean absolute error. which is exactly what it sounds like. That is mean absolute error. It's just the absolute error between what you want and what you have, and then the mean of all of those. Between the predicted flow, so from our optimized representation, and the supervising input flow derived from running optical flow. Okay, so Fi to j, this is the one that they're getting from the raft technique, or whatever they call it, raft technique up here. Fi to j, this is the predicted flow, or the supervised flow, where it's not actually correct, right? So that's an important thing to realize, is that usually in supervised learning, you can make the assumption that the supervising target is actually correct. So if you're doing classification between dogs and cats, you can generally make the assumption that the person who labeled the image as a dog, that's actually the correct label for that image. But here, the target that you're trying to track with this mean absolute error is actually not perfect, right? It's an estimate. Okay, but basically you have your predicted flow here minus your supervised flow, your target. Sometimes it's called in supervised learning. What you're actually trying to predict is actually usually called the target. Here, these double parallel lines with a 1, that means just basically an L1 loss, which is what mean absolute error or absolute error is just an L1 loss. You're summing this over all predicted flows in this set of omega f. Omega f is the set of all the filtered pairwise flows. So this might be every single pixel. I doubt it's every single pixel. It's probably a little bit sparser. In addition, we minimize a photometric loss defined as the mean squared error between the predicted color and the observed color. Okay, so you have a mean squared error between the flow, and then you also have a mean squared error between the predicted color and the observed color. So you see here how mean absolute error, it's parallel bars with a 1. And then you have mean squared error, and now it's parallel bars with the 2. So this is squared error versus just absolute error. But same thing, you're basically subtracting the predicted with the target, and you're doing it over all points inside this set omega. Omega p is the set of all pixel locations over all frames. This can be absolutely huge, so I assume they probably filter that. Last, to ensure temporal smoothness of the 3D motion estimated by m theta, we apply a regularization term that penalizes large accelerations. Yeah, I don't know. You know, this is just another prior. Regularizations are a way that you put priors into your optimization, but are large accelerations technically a bad thing? Like, sometimes you're going to have large accelerations. Let's say you had a video of like a UFO that was like moving very quickly, right? At that point, this regularization term would actually be bad because it would penalize quickly moving across the video. But I think in some videos, maybe someone's like throwing a ball or something, you're going to have very large accelerations. Given a sample 3D location in frame I, we map it to frame I-1 and now I+1, yielding 3D points xi-1 and xi+1, and then minimize the... I'm going to sneeze here. Or not. I don't know why my nose gets so itchy when I stream. But, okay. They have a 3D location xi, and then they're basically mapping it to the frames. Fuck. And then the distance between those 2 points should obviously be as small as possible, right? Because if you're mapping the same location to 2 frames, ideally those 2 mappings should be the same. Or no, never mind. Here, this term is about penalizing large acceleration. So if the distance of these 2 points is very large, it means that the point moved a lot during those 2 frames, and they want to reduce that. They don't want points moving a large distance in between frames. All right, so they take those 3 losses. They take basically the flow loss, they take the color loss, and then they take the regularization for acceleration, combine all 3 of those into 1 loss, and then that's the loss that's used for this optimization process. The intuition behind this optimization is to leverage the bijections into a single canonical volume G, photoconsistency, and the natural spatiotemporal smoothness provided by the coordinate-based networks to reconcile inconsistent pairwise flow and fill in missing content in the correspondence graphs. Balancing supervision via hard mining. So what is mining? Mining is not mining of cryptocurrency here. Mining generally refers to, or at least what they're going to be talking about here, is mining examples. So one thing that you might have heard is negative example mining, hard negative mining. So this is picking points in a distribution of data for a specific purpose. So maybe you're doing some kind of face detection, right? Negative mining would be finding pictures that are very different from that, or maybe close but at a specific thing. So let's see, for example, hard positive samples, hard negative samples. I don't think any of these pictures explain it super well. All right, let's see what they describe it as. Exhaustive pairwise flow input maximizes the useful motion information available to the optimization stage. However, this approach, especially when coupled with the low, can result in an unbalanced collection of motion samples in dynamic regions. So what they're saying is that, right, they started from an initial guess based on this classic algorithm Raft, right? But then they take the guesses of these correspondences and they filter them, and then they also chain them. And what they're saying here is that because we took the answers from this classic algorithm and then we filtered them out, the actual data set that we're going to be using, this starting point that we're starting from, is actually going to be weird. There's going to be a bunch of points in certain objects. There might be no points in other objects. It might just be weird, like rigid backgrounds might have less points than others. So it's basically like it's not a very necessarily a good starting point, is what they're saying here. Rigid background regions typically have many reliable pairwise correspondences, while fast-moving and deforming foreground objects often have many fewer reliable correspondences after filtering, especially between distance frames. This imbalance, right, it's imbalanced data set, or imbalanced starting point, can lead the network to focus entirely on dominant simple background motions. Okay, so the points in the background, they don't move a lot, so they're easy to predict. So maybe your filtering process kind of biases towards these. Ignore the challenging moving objects that represent a small portion of the supervisory signal. Right? So the signal that you're using right here, they're saying they're training in a supervised way, because why is it supervised? Because they're starting from these points and they're assuming that they're correct even though they're not, right? This is quite tricky, is they're doing supervised training, but they're doing supervised training with pseudo labels, basically. And not only are they doing supervised training with pseudo labels, but the data set that they're using that has the pseudo labels is actually imbalanced. So you're going to have more labels for background, less labels for foreground and fast-moving objects. We propose a simple strategy for mining hard examples during training. Specifically, we periodically cache flow predictions and compute error maps by calculating the Euclidean distance between the predicted and input flows. Euclidean distance between the predicted and input flows, that's basically this. Predicted and input flows and the distance between them. I mean, that's literally what this is right here. We use these error maps to guide our sampling process during optimization, such that regions in the higher are sampled more frequently. All right, here you go. So this is the type of hard mining that they're doing. In this case, they're mining specifically for examples where the error between the predicted flow and the supervisory flow are big. So they're saying, okay, well, we have this loss over all these points. Some of these are going to have a big difference. Some of these points are going to be the difference between the predicted and the supervised is huge. And at that point, you want to sample more of those, right? Because if the distance is big, that means there's a high error. And they're saying that they get high errors on fast-moving foreground objects, which is honestly the type of stuff that they want to be tracking. We compute these error maps on consecutive frames where we assume our supervisory optical flow is most reliable. Okay, so of course, because they're using these kind of like pseudo labels, right? They're basically using optical flow from a separate technique. They don't want to be doing this between frames that are further apart, because the technique that they use, Raft, is going to work not as well for frames that are far apart. So they're going to use frames that are close together. Okay, so let's see. Before we go into the implementation, just kind of summarizing this, I generally don't like this. I feel like, you know, I liked the prior that they were talking about here. I liked that they were basically just applying a nerf with a slightly different kind of prior and relaxing it. Like I found this to be kind of beautiful, but this optimization process they described here, where you have basically this two-part thing where you're initializing an optimization process with the output of a previous flow prediction technique, having these 3 losses with different weights, doing this hard mining. Like, this is just a bunch of tricks, right? These are a bunch of engineering tricks, hard mining, multiple losses, different weights on the losses. Like, I don't like that. That's extra complication, extra annoying things, like more moving parts. And generally, the more moving parts, the more complicated your things are, the more difficult they are to re-implement, the more difficult they are to understand, and the more difficult they are to really use in a separate technique or use for some other thing and build upon. So I don't like all this extra complexity that they introduced with these loss functions and negative example mining. All right, implementation details. Network. Our mapping network, M theta, consists of 6 affine coupling layers. We apply positional encoding, good old positional encoding, with 4 frequencies. Positional encoding tells you gives you basically a vector that represents the position of, in this case, points in the pixel space, right? And positional encoding is basically usually this sum of sines and cosines. So, yeah. You basically have these sines and these cosines, and you're basically, it's kind of almost like a Fourier series in my head. Like, this is kind of how I think about it. But some of you that are more gifted in math might be cringing at me using the term Fourier series to describe positional encodings. But basically, you're adding these sine and these cosine waves to represent the position of something in something, right? So here they're saying they have 4 frequencies of sines and cosines that they're using in this positional encoding. Before computing the scale and translation, we use a single 2-layer MLP with 256 channels. That is a very small little neural net, to be honest, implemented as a GabberNet architecture to compute the latent code. This is the latent code that they use to condition the M. So here, M theta, the invertible network that maps from xi to u. It's being conditioned on this latent code, psi I. So that's what they're referring to here, is that latent code is generated by this 2-layer MLP. For each frame I, the input to this MLP is the time. Okay, so the latent code is literally just the time. The dimensionality of the latent code is 128. The canonical representation F theta is also implemented using GaborNet, but with 3 layers of 256. What the fuck is a GaborNet? GaborNet. Deep convolutional modified architecture that focuses on improving complexity. The filters in the first layer are constrained to fit the Gabber. I think Gabber filters, right? That's a thing. Yeah. So these are just simple primitives again. An introduction to Gabber filters, again, these like hard-coded filters that people would design back in the day and then convolve, and then you would be able to find edges and stuff like that. And then I guess a GabberNet is like maybe a neural net where the the lower feature maps are basically just like hard coded to those Gabber filters. Got some Russian dudes here. Moscow Institute of Physics and Technology. This is a very old paper. The filters in the first layer of the network are constrained to fit the Gabber function. Okay, so basically it's a convnet where the first filters are basically Gabber filters. Okay, so that's what a Gabber net is. So not only is this actually kind of a really tiny neural net, but it's also like the first layers are basically fixed to these Gabber filters. We normalize all pixel coordinates pi to the range -1 to 1. Right, so of course, if you're doing anything with neural nets, you want to basically normalize your inputs, and even within the layers of your neural net, right? Layer norm, batch norm, all of those are basically what you're doing is you're normalizing within a batch, normalizing within a layer, and so on, and normalizing to make it nicely shaped so that you can tell the outliers from the not outliers. And one kind of black box theory is that, or one theory to explain the black box nature of neural nets is that largely what they're doing is they're basically, you just have to recognize outliers and not outliers, which is kind of how your brain works too, right? Your brain, the neurons in your brain, they're either spiking or they're not. It's like they're either just receiving a bunch of inputs and then they decide to do nothing with that, or they receive a bunch of inputs and then they decide to fire and spike. And artificial neural networks kind of, generally they're more complicated, right? Because the way that your activation functions work, it's like, it's not just firing or not firing. They like produce more signal or less signal, right? So a neural net, if it gets a bunch of signals that kind of add up a little bit, it'll fire a little bit, or an individual neuron. But if that little neuron receives a bunch of positive signals, it'll fire more, right? So like in an artificial neural network, the neurons can have a little bit more nuance to their actual activation, like what they're passing forward to the next neuron in the next layer, right? It can be a little bit more nuanced, but I think in your brain, it's not like this, right? I think neurons don't have this notion of I can fire more or I can fire less. I think in your brain, it's basically they're either firing or they're not. So, okay, I kind of got distracted there. Let's get back to this. We set the near and the far depth range to 0 and 2, right? So they don't actually have a, again, their quasi 3D representation is not actually a 3D representation. So whenever they talk about depth, they're not actually referring to the actual physical depth. They're referring to basically this fake depth that they've been talking about, which is kind of like a foreground, background kind of situation. Local 3D space in each frame as -1 to 1 times 0 and 2. So basically the local 3D space, this like quasi 3D space is -1 to 1, and this little 2 there means that it's basically -1 to 1 on the X and Y, right? X and Y, the width and the height of the image. And then there's this depth of 0, 1, and 2. Or 0 to 2, sorry. I don't know why they didn't do 0 to 1. Why 0 to 2? Right? Don't you feel like it should have been 0, 1? It's kind of weird. While our method can place content at arbitrary locations in the canonical space G, we initialize a mapped canonical location by m theta to be roughly within a unit sphere to ensure well-conditioned input to the density and color network. That's not good. More biases, right? More priors here. Now they're using a unit sphere prior. So when they initially pick these points in this local 3D space, they're making sure that the locations are within a unit sphere of the point in a different frame of this. So this is probably how they do this filtering. It might be one of the filtering techniques that they used. To improve numerical stability during training, we apply contraction operation as in MIP Nerve 360. I don't know what this is, the contraction operation. Training. We train our representation on each video sequence with the Atom Optimizer for 200K iterations. In each training batch, we sample 256 pairs of correspondences from 8 pairs of images, resulting in 1024 correspondences in total. Okay, so batch size is 256, where each pair is 8 pairs of images. We sample K equals 32 points. That's a lot of points along array. I think in the NERF papers it's 16 is what they use, but here in these figures you see 7 points, but they're actually sampling 32 points, which is actually a lot, right? Because in this thing, their K isn't even corresponding to depth in terms of the actual depth. It's corresponding to this like kind of like pseudo depth, right? Which is just foreground, background. So it's kind of weird that they have such a high number of points along this ray that just goes straight into the depth, right? If you remember here, the ray itself starts at some origin, which is the point, and then goes to 0. And the direction is 001, which means it just goes straight into it. So they sample 32 points along this thing that just goes straight into the depth. It's a lot. Evaluation. Okay, so they evaluate on this TADVID benchmark, which we tried to look up and couldn't even find a single fucking thing for it. So kind of an obscure benchmark that they used. TADVID consists of both real-world videos with accurate human annotations of point tracks, and then some synthetic videos with perfect ground truth point tracks. Again, if you have synthetic videos, you know the exact perfect ground truth. We evaluate on the following data sets. Davis. Okay. So we got clips 34 to 104 frames. You got kinetics, which is about 250 frames with around 26 point tracks per video. RGB stacking, where each video has 250 frames and 30 tracks. So these are very short little videos, right? These are maybe 5 seconds, something like that. Which isn't great, right? Because it's kind of what we were saying before, where because they're projecting every single point in every frame to one quasi 3D representation or space that represents every single point at every single frame. That means that the entire video has to fit into this one quasi 3D representation. And I think that that's only really going to work for like little 3 to 4 second videos. I think if you tried to do this with a 7-minute video, it wouldn't work, right? Because like the camera would change completely, right? Like think about it this, right? Think about this one here where they have this dog moving across, right? Here you have these flowers that appear, right? And they're there briefly, but think about it this way. In this frame right here, the flowers are no longer part of this frame, but in the canonical 3D space, there's a point that represents those flowers, right? So the canonical 3D space is using some of its capacity to represent a point in this video that isn't going to appear in this video ever again, right? So at some point you're going to run out of capacity in that space, that canonical quasi 3D space that they're using, right? Especially the longer and longer the videos go, the more you're going to try to fit crap into there, and it's just not going to fit anymore. So yeah, I think one thing that I'm not liking about this is just how short the videos are. We adhere TAP benchmark, so resolution they're using is 256 by 256. Following the TAP, we report both the position and occlusion accuracy. Okay, so these are kind of quantitative metrics that they're going to use here. Less than delta X average, so this is just a fancy delta here. Measures the average position accuracy of visible points across 5 thresholds. Okay, so if the point is within 4 pixels of the original point, then it counts as a as a hit, I guess, and then they have this basically this threshold where the threshold is the fraction of points that are within X pixels of their ground truth position. Okay, so this is like some kind of like a little bit hard-coded, to be honest, accuracy metric here with a threshold. It's kind of like similar to a bounding box. When you're have like a bounding box accuracy, generally you have this number called the IOU bounding box, the intersection over the union, right? So anytime you see like a COCO metric, at some point someone had to say, okay, well, what counts as a hit? Does this count as a hit? Like, how much overlap does there need to be before we can count this as an accurately accurate bounding box versus not accurate bounding box? So there's a similar kind of thing here where they have some random basically threshold that some human picked of 1, 2, 4, 8, and 6, where they say, okay, if it's within this amount of distance from the ground truth, then we're going to count it as accurate. But again, these numbers are kind of like randomly picked by some human at some point. Jacquard, average Jacquard, so values both preclusion on the same threshold. Categorizes predicted point locations as true positives, false negatives. Defines the ratio of true positives to all points. False positives, ground truth. Okay, so basically some kind of ratio of true positives based on the occlusion as well. Occlusion accuracy evaluates the accuracy of the visibility and occlusion. Okay, so this might be more like a classification accuracy, because visible, not visible is just going to be a binary, right? It's either 0 or 1. So this is almost like a binary classification accuracy here. Temporal coherence evaluates the temporal coherence by measuring the L2 distance between the acceleration of ground truth tracks and predicted tracks. So the problem with this, acceleration is measured as the flow difference between adjacent video frames for visible points. So this is what they were doing here, right? So they had this regularization term that basically minimizes the acceleration between 2 points, right? Which is basically the distance between these 2 points. So they have a regularization term that literally minimizes this acceleration. And here they are using acceleration as a metric. So of course, this is going to be improved by the fact that you have an explicit regularization loss that is minimizing this thing here. But I would say that acceleration and temporal coherence aren't necessarily the same, right? To me, temporal coherence is a superset of acceleration. You can have temporally coherent frames whereas an object accelerates very quickly. So I think there's an unfair kind of assumption that minimizing acceleration is a proxy for temporal coherence, whereas I feel like acceleration is acceleration and then temporal is temporal. Okay, I'm going to get off my little high horse there. We compare our method with various types of dense correspondence, including optical flow, feature matching, multi-frame trajectory, and so on. Of course, they're going to compare to RAFT. Apparently, there's also a RAFT-C and then also a RAFT-D. We always use the previous flow prediction as initialization for the current frame. Okay, so RAFT chaining is this chaining where they chain the predictions between consecutive frames. And then RAFT-D is direct raft, so without this chaining. They have this PIP technique, which they were talking about, that looks at a temporal window of 8 frames. And then again, you need to use chaining if you want to chain motion trajectories beyond the 8 frames. They're going to compare to flow walk, multi-scale contrastive random walk. The fuck is this? I've never heard of this, but this sounds pretty cool. Is this a recent paper? 2022? Yeah, this is pretty recent. Okay. That's kind of cool. It's a CVPR paper from 2022. It uses contrastive learning. That's interesting. And, of course, TAPNet. And deformable sprites, which was another one that they mentioned. This is a layer-based video decomposition. It uses a per-video test time optimization. Oh, like our method, it's a per-video test time optimization. However, it does not predict directly produced frame to frame, and the mapping from each frame to a canonical texture is not invertible. A nearest neighbor search in texture image space is required. This is going to be gross. Okay. So some of these techniques that they're comparing to directly predict occlusion, but other ones do not. So they're not going to be able to use the occlusion accuracy for some of these. We detect occlusion, blah, blah, blah. Comparisons, quantitative. We compare a method. Our method achieves the best position accuracy, occlusion accuracy, and temporal coherent consistency across different data sets. Okay, so Raft C. Yeah, if you look at this, so this is what it's initialized. This is the first frame. And then you can see that Raft C, as soon as the person goes behind this post, every single one of these points gets stuck. So it's almost like the person just goes through, and then all of these points get stuck, right? And think about why would this happen? It probably happens because this technique, this Raft C, is basically looking at frame by frame, right? So as soon as the person goes behind the column, every single one of those points now suddenly becomes attached to the column. And then when you do frame by frame after that, you're just comparing column points to column points, column points to column points, and it kind of just gets stuck. So this is a very nice little visualization there. And you see that whenever this person comes back through, some of the points get stuck to the person. But at this point, some of these points are like hard stuck to this column. So that's a pretty cool little visualization there. Here you have this kind of like busy scene. These are some of the hardest things to do, honestly, if you're in the kind of tracking world, like these kind of like busy street scenes where you just have like all these people like kind of moving all over the place. This is like the hardest shit to do, to be honest. Like re-ID in this is like fucking impossible. Okay, so here they're showing you the occlusion, how as soon as you have this guy and he kind of like walks in front of the frame, it kind of like throws off all the tracking. But of course, this paper, it manages to track the person. Here you have an interesting kind of situation where the camera is zooming. So rather than an object staying the same relative size and then moving across the frame, you now have this, the object is going to get bigger and bigger, which actually you see the technique here does manage to do that. You see how the distance between these points actually gets wider because it understands that the thing is moving closer, versus this TapNet, it kind of just quickly goes out of hand. You see how like these points just kind of become nonsense. So these are very impressive results. Of course, these are going to be cherry picked, but compared to approaches that directly operate on non-pairs of query and target frames, our method achieves significantly better temporal coherence across due to our globally consistent representation. Compared to chaining-based methods, our method achieves better tracking, especially on longer videos. Is a 4-second video a longer video? I don't know. That seems like still pretty short to me. OmniMotion enables tracking points through extended occlusions. Our method also outperforms the test time optimization approach of deformable sprites. We compare our method qualitatively. Providing all plausible locations, please refer to the supplementary video. Okay, so here we have the actual numbers. So this is average Jacquard. Is that what this was? AJ is average Jacquard. Then OA is occlusion accuracy, and TC is temporal consistency. So this is the threshold. So this is kind of tracking. This is occlusion. And this is temporal consistency. And it does seem like their method does pretty much the best on everything. But it's kind of unfair to compare because remember how their method, they're initializing it from the results of a previous method. So they're using Raft, and then they're using the answers of Raft to initialize their method. So, of course, it makes sense that their method is going to be just better than vanilla Raft, right? And of course, it makes sense that their method based on TAP is going to be better than TAP. So really what you need to be comparing here is this number here. It's basically the Raft method gives you an AJ of 50, and then by using their refining technique, which this paper should really be called a refining technique, you get another extra 5 points here. but this is what I'm looking at. You see this 85 versus 89. So it seems to me like most of the heavy lifting is coming from Raft and from Tap, right? Like look at this 61 versus 68. 48. Here you have a little bit more, 48 versus 67. 76 versus 85. So here you're seeing a little bit more. Here you're getting almost like a 10% improvement by using this technique. But in some of these data sets, the difference between Raft and this technique initialized by Raft is actually not that much. Like for example here, 85 compared to 87. Like you're really not doing that much better. And these arrows here, by the way, these mean higher number is better. These arrows mean lower number is better. Higher number is better. Lower number or higher number is better. Ablations. We perform ablations to verify the effectiveness of our design decisions. No invertible is a model variant that replaces our invertible mapping network with separate forward and backward mapping networks. Okay, so remember that they picked this real NVP because it's a network that you can invert. It's a network that allows you to go from, it's based on these affine transformations. It allows you to go from a data space into a latent space, and then from that latent space back to the data space with the inverse of that, right? Because you can take the inverse of an affine transformation. So they chose that for M of theta, but they said, okay, well, what if we chose two separate things rather than having this invertible neural network? We just choose a normal neural network that has one for the forward and one for the backward. And that's what no invertible is. And actually the no invertible does absolutely terrible. Look at this. This is dog shit. Interesting that it does good on occlusion, but it does very, very poorly on these AG and this delta average, so the tracking. We add cycle consistency loss. It still fails to construct a meaningful canonical space. And it can only represent simple motions of the static background. No photometric is a version that omits the photometric loss LFO. So this is the loss that pulls the colors together, so makes the colors consistent between different points. You can see how this one does seem to give you a pretty good improvement here. Or no, it doesn't. Never mind. Whether or not you have the color, it does actually, look at this, it even makes, it doesn't seem like the color loss is adding that much. And then uniform sampling replaces our hard mining sampling strategy with a uniform sampling strategy. So the hard mining sampling strategy, what they were doing is they're basically picking the points that have the biggest error, and then using, basically sampling more of those whenever you're actually performing training batches. So rather than doing this hard mining where they're kind of picking, purposefully balancing the imbalanced data set, uniform sampling makes it sound like it'd be more balanced, but because the data set is fundamentally imbalanced, uniform sampling actually results in a less uniform training batches. So uniform sampling here actually means imbalanced training batches. And you can see that it actually doesn't actually matter that much either. We show pseudo-depth maps generated from our model to demonstrate that learned depth ordering. Note that these maps do not correspond to physical depth. Nonetheless, they demonstrate that using only photometric and flow signals, our method is able to effectively sort out the relative ordering between different surfaces, which is crucial for tracking through occlusions. More ablations and analysis are provided in the supplementary materials. So this is the pseudo-depth. And I think this kind of tells you a lot, right? Because it's like we keep mentioning that the depth that they're using is not real depth, right? It's more like foreground, background, and you can see here how that actually kind of maps, right? Where it's not, this isn't like a real depth where it's basically saying how this person and this person are, like the distance between this guy on the moped and this guy on the moped should be different than the distance between this guy on the moped and these people here. But with this pseudo depth, that's not the way it is at all, right? The person in the foreground is kind of at the same pseudo depth as the person here, which is like right in front of the camera. So this is the kind of weird pseudo depth prior that I think is actually kind of a clever idea. All right, discussions and conclusions. Like many motion estimation, our method struggles with rapid and highly non-rigid motion, maybe because you're using that acceleration regularization term. Maybe if you got rid of that, it would work a little bit better for rapid motion. Pairwise correspondence can fail to provide enough reliable correspondences due to the highly non-convex nature of the optimization problem. Non-convex means that it's convex versus concave. Convex, you could think of like a smooth, like little here. Concave versus convex. Yeah, so these are more like lenses. I need optimization. Yeah, so you see this convex shape here. When you have an optimization problem that is convex, right? This is actually even better. No matter where you start, the shape of this optimization problem leads you to the solution, right? It's like you basically can very easily follow gradient descent to the minimum of this function, right? Versus a non-convex optimization problem, you have a lot of these kind of like, it's not nicely shaped, right? So you're going to end up in these little local minimas, right? If you just follow gradient descent. So that's what they're talking about here. Because of the highly non-convex nature of this optimization problem, the training process can become trapped at suboptimal solutions. Here's the trapped in a suboptimal solution here, also called a local minima, right? You get stuck here. You never actually get to the global. Our method in its current form can be computationally expensive. I mean, tell me about it. It's probably even more computationally expensive because you literally have to use you have to basically initialize it from a starting point, which is itself another type of approach. We believe the scalability can be improved by exploring more efficient alternatives to exhaustive matching. Vocabulary trees or keyframe-based matching. Other methods that utilize neural implicit representations. We propose a new test time optimization method for estimating complete and globally consistent motion for an entire video. I feel like they're kind of not talking about the fact that it needs to be initialized with an already existing set of pairwise correspondences. Includes a quasi 3D canonical volume and a per frame local canonical bijections. OmniMotion can handle general videos with varying camera setups and scene dynamics and produce accurate and smooth long-range motions through occlusion. Our method achieves significant improvements over prior state-of-the-art methods, both qualitatively and quantitatively. Cool. Is there anything here in the okay, maybe showing you some mistakes here. Training details. In addition to the photometric loss LFO, we introduce an auxiliary loss. Damn. Okay, so you know how I was complaining that they have too many weird special losses? Well, there's another secret special loss, LP grad here, that's minimizing the distance in between these colors. Network architecture of the mapping network M theta. So this is the M theta is the invertible NVP, real NVP neural net, which is basically these affine transformations. So the first affine coupling layer. See here how this is the latent vector that they condition on. So they're taking the X and the Y position in pixel space. They're using this PE, which is a position encoding. So the position encoding of the X and Y in the pixel space, plus this latent conditioning vector that's fed into a multi-layer perceptron. You get this S and the T, which are basically the scale and translation probably. So S and T are probably the actual affine transformation. And that gets used to change this Z. Okay, we don't know exactly what the S and the T are. I'm guessing those are the actual affine transformation, but I'm not 100% sure. Cool. So that's it. That's the paper. Let me see if I can do a quick summary here. All right. So today we read Tracking Everything Everywhere All at Once. This was work that comes out of Google, Cornell, and UC Berkeley. This was a tracking paper that builds on top of existing optical flow and structure from motion work. It calculates pairwise correspondences between frames in a video in such a way that you can create pixel trajectories for any pixel in the video. It has a very interesting prior where it creates this canonical 3D coordinate space, which they're calling G here. The space actually, interestingly, is not a 3D space entirely, so it's very similar to a NeRF, right? But it's not a NeRF. A NeRF is actually, the volume in a NeRF is an actual 3D space. The volume here is basically pixel width, pixel height, and then this like kind of weird depth that represents foreground, background, and so on. And they have these neural networks which basically map from this canonical space to the actual pixel space. And these neural networks are invertible, right? Because they use a special type of invertible neural network called let me get the exact name, called a real NVP, which is basically a bunch of stacked affine transformations, and affine transformations are invertible. One thing I didn't like is that they have to initialize their algorithm with the output of a previous approach. So they have to use an already existing flow estimation algorithm, in this case Raft, but they also try a couple other ones like TAP. They have to use a different one to even initialize and start this one. So I really think that they should call this a refining process rather than a motion estimation process. This is refining the output of a previous one. And I also don't like that their optimization process is actually quite complicated. There's a bunch of different losses here. They have a flow loss, they have a color loss, they have a regularization loss. If you actually scroll down to the appendices, they even have another loss that they don't even talk about in the paper. They have this extra p-grad loss. So there are 4 different losses with different weights. And not only that, but then they also have to do all the kind of extra complicated stuff like hard negative example mining in order to properly balance the pairwise points that they're using in this optimization process. But yeah, despite that complexity, they do get pretty good. I like qualitatively, these results are very impressive, right? These examples here are qualitatively very good. I think quantitatively, the results are less impressive. If you look at the quantitative results, the difference between the existing tracking methods and their methods they're actually very similar, right? Which goes to show you that most of the heavy lifting is being done by the approach that they're initializing from, such as Raft or TAP, and really all their approach is doing is just kind of giving you an extra 2%. So, yeah, that's that. Interesting paper. I like this 2.5, this kind of like weird NeRF where the depth isn't the real depth. I think that's an interesting idea. I wonder if you could use this prior in some interesting way for image generation, 2D image generation with diffusion models. There's a lot of things like that where I feel like you could maybe fit in an idea similar to that. But other than that, really cool qualitative results. Quantitative results kind of not as impressive. And then I think the complexity of this paper is a little bit too much complexity. I wish it would have been a little bit simpler. But other than that, pretty cool stuff. Thank you guys for listening. Thanks for the comments. Thanks for engaging. Thanks for watching. And have a great week. Hope you guys have a good one.